Have you ever imagined stepping aboard a spacecraft and leaving the blue-green glow of Earth behind, heading out toward the worlds that make up our solar system? The trip to the moon, 238,000 miles away, took 3 days back in the Apollo era. So we tend to assume, if 3 days got us to the moon, how long would it take to reach our planetary neighbors? 10 days? A month, maybe? The real numbers are, for the most part, far stranger than that intuition. Today, we're going to travel across the solar system planet by planet and work out, using the real constraints of orbital mechanics, how long each trip would actually take and why every single minute on board would represent a genuine feat of human engineering. Before we start, try guessing for each planet before I give you the answer. I'm curious to read your calculations in the comments. I know some of you like to check the math. Before we chart our routes, we need to talk about orbits. Planets don't trace perfect circles. They trace ellipses. Sometimes a body swings closer to the sun, perihelion, and sometimes it drifts farther away, aphelion. And planets don't all move at the same speed either. The farther a planet sits from the sun, the slower it travels. Picture planning a bus route where every single stop is also moving. That's exactly how interplanetary missions work. Flying straight at your target makes no sense, because by the time you arrive, the destination has already moved. That's why engineers use curved paths instead. Like the Hohmann transfer, one single burn places the spacecraft on an orbit that will meet its target at exactly the right point, while saving fuel. Whenever possible, engineers combine that trick with a gravity assist. The spacecraft skims past a planet or moon, stealing a little of its orbital energy, and picks up speed without burning a single extra drop of fuel. Mercury. How long would it take to reach Mercury? The question sounds simple, but behind that curiosity is a planet that, despite being the smallest in the solar system, holds essential clues about the cosmic infancy that shaped everything around us. Because it hugs the sun so tightly, Mercury acts like a window into the past. Its crater-scarred surface, its traces of ancient volcanism, and an active metallic core that sustains a surprisingly powerful magnetic field for such a small world. Studying that field, understanding what's inside it, decoding the scars on its crust, that's not just curiosity, it's a direct way to illuminate how planets form and evolve. There's even been talk of the possibility of liquid water there, in the distant past. As extreme as that sounds, if it ever really happened, it would open up a fascinating question, whether conditions favorable to life could have briefly emerged there too. But before studying anything, you first have to get there. And the trip depends on a whole set of variables: speed, the distance between planets, the type of propulsion, and above all, braking at exactly the right moment. For reference, the Parker Solar Probe has already topped 430,000 miles per hour, 692,000 kilometers per hour, during its closest passes by the sun. And even so, on an optimistic trajectory, it would still take us more than 4 months to reach Mercury. Why? Because the distances never stop changing. On elliptical orbits, planets are constantly drifting closer and farther apart. There's no single fixed distance between Earth and Mercury. When the two worlds line up on the same side of the sun, inferior conjunction, the route shortens and can drop to just tens of millions of miles. In other alignments, the gap doubles or more. Mercury, by the way, has the most eccentric orbit in the solar system, an eccentricity of about 0.21, while Venus is far more circular, at about 0.06. And that alone is enough to scramble every calculation. In practice, nobody just points a rocket at Mercury and hits a button. The trip has to be choreographed like an actual physics ballet. Launch windows, transfer trajectories, and almost always, gravity assists. That's exactly how every mission that's gone there did it. In 1973, Mariner 10 borrowed a gravitational boost from Venus and took about 6 months to make its first flybys of Mercury, delivering the very first close-up images. Decades later, Messenger, launched in 2004, ran a marathon of maneuvers past Earth and Venus before finally settling into orbit around Mercury, a feat that took roughly 6.5 years of travel, followed by 4 more years of study until it ran out of fuel. Today, BepiColombo, the joint ESA-JAXA mission launched in 2018, is making its way there using solar electric propulsion combined with multiple gravity assists off Earth, Venus, and Mercury itself, before finally settling into place. Notice the pattern that keeps repeating. Flying past is easy. Entering orbit is hard. To let a planet's gravity capture it, a spacecraft has to arrive slow enough relative to that planet, and in the vacuum of space, braking is expensive in terms of energy. Can the trip be shortened? Partly. Gravity assists move the clock forward, but they demand surgical precision. Get the timing wrong, and the spacecraft misses the very planet that was supposed to help it. And unlike Earth or Mars, Mercury doesn't have a real atmosphere to help slow a spacecraft down through aerobraking. The descent rests almost entirely on the engines. Add in the extreme thermal stress of being so close to the sun, and you start to see why long, slow flights end up being, paradoxically, the cheapest way to get there. Venus. When the question turns to Venus, the glow gets brighter and the story heats up, literally. Venus is the brightest object in the sky after the sun and moon. It shines because its atmosphere reflects an enormous amount of light, and because it cycles back close to Earth on a regular basis. But once again, close is a moving target. The orbits are elliptical, and the alignments keep shifting. At inferior conjunction, when Earth and Venus sit on the same side of the Sun, the distance drops to a minimum that repeats roughly every 8 years, thanks to the two planets' near-periodic dance. Over the long run, the average distance swings wildly. So no, nobody serious answers, how far is Venus, with a single number. What we can say is that Venus has the most circular orbit of any planet, which makes its behavior far more predictable than Mercury's. Why go to Venus at all? Beyond being the hottest planet, surface pressure roughly 92 times Earth's, oven-like temperatures, it may have actually been habitable billions of years ago, before a runaway greenhouse effect dried the whole world out and turned its crust into a geological pressure cooker. To probe that past, humanity has sent an impressive number of probes there, with a historical success rate that actually beats Mars. The Soviet Union led the way with Venera 1 in 1961, though contact was lost early. It's estimated to have passed within about 60,000 miles of the planet after 97 days of flight. Mariner 2 in 1962 pulled off the first successful flyby in 110 days. In 1978, Pioneer Venus 1 entered orbit after a 198-day journey. ESA's Venus Express traveled for 153 days in 2005 before settling into orbit. Why such variation? Because arriving isn't the same as staying. Flyby missions can take faster routes. To settle safely into orbit, missions generally take longer, more fuel-efficient paths. On average, successful missions to Venus have taken between 4 and 6 months, with records around 109 to 110 days, and longer routes stretching close to 200 days. Aim higher with more efficient engines, and there's no reason trips of 60 to 80 days couldn't happen someday. But landing and surviving on the surface is an entirely different story.
The only images ever taken from the ground came from Venera 9 and 10, which lasted just 53 and 65 minutes before succumbing to the heat and the corrosive sulfuric acid.
Mars. When the destination becomes Mars, the whole tone of the question changes. It's no longer just how long, it's how and with whom. The path to the Red Planet has been shaped by both cooperation and competition between NASA and SpaceX. The former makes safety and redundancy its North Star. The latter bets everything on technological leaps and aggressive reuse. And oddly enough, the two approaches complement each other. Let's talk distance. In 2003, Earth and Mars came within about 35 million miles of each other, one of the closest approaches on record. At other times, that gap doubles or more. If you play with the speed of light, travel time would range from about 3 minutes at the closest to more than 20 minutes at the farthest, averaging around 12.5 minutes for a beam of light. For an actual spacecraft, the math changes completely. New Horizons, on its way to Pluto, left Earth traveling at about 36,000 miles per hour. At that pace, Mars could be reached in roughly 162 days at average distance, up to 289 days in the worst-case alignment, and, in a very favorable alignment, as little as 39 days, in pure theory. And if you used the Parker Solar Probe's peak speed, purely hypothetically, the math would drop to about 93 hours in the best case, and close to 29 days in the worst. But that's just a thought experiment. Real trajectories aren't straight lines, and cutting through the sun obviously isn't on the table. In reality, engineers use a Hohmann transfer, that elegant ellipse that leaves Earth's orbit and just kisses Mars's, with a launch window opening every 26 months. It's the most fuel-efficient method we know. The trip usually takes around 9 months, and a full round-trip plan, with a stay on the surface and a return window, can add up to 21 months total. Trading efficiency for speed means burning a lot more fuel, cutting into payload, and dealing with the psychological toll of months packed into a narrow cylinder far from Earth. That's where the Raptor engines and Starship come in. Very high thrust, reusability, lower cost per attempt. If those promises hold up, the question, how long to Mars, stops being an almost insurmountable barrier and becomes simply a matter of scheduling, budget, and acceptable risk. Jupiter. So why would anyone want to go all the way to Jupiter? Even without a solid surface, the solar system's largest planet is a living laboratory. Continent-sized storms, a colossal magnetic field, and above all, a system of moons that looks like a miniature solar system of its own. Europa, Ganymede, and Callisto may be hiding global oceans under their ice, possibly the best place to search for life beyond Earth. But is it far? Because Earth and Jupiter follow different paths, the distance between them is constantly changing. At best, about 365 million miles. At worst, close to 600 million. On average, around 480 million miles. That's such a long road that if you drove at 70 miles per hour without ever stopping, it would take you centuries. The trip depends, once again, on alignment, and above all, on how much energy you're willing to spend accelerating and then braking. Looking at past missions helps set expectations. Pioneer 10 got there first, a direct route, about 640 days. Pioneer 11 and the Voyager probes also moved fast and passed relatively close, within tens of thousands of miles, but they didn't stay. They used Jupiter's gravity as a slingshot to gain speed toward the outer solar system. Galileo, on the other hand, took its time, nearly 6 years to enter orbit, on a Vega-style route, gravity assists from Venus and Earth, in order to arrive at just the right speed and stay there for years. Time and fuel paid up front, in exchange for extremely high-quality science. In 2006, New Horizons cut the trip down to about 405 days to Jupiter, using the giant's gravity to slingshot toward Pluto, the flyby even handing it a bonus of roughly 9,000 miles per hour. And today, Juno is closely studying Jupiter's magnetic field and interior, on a mission that also demanded patience to get into orbit and stay there. Now let's talk about humans out there. And this is where our current limits become obvious. If you generalize the most efficient trajectory math, a trip to Jupiter could take close to 6 years. Just for food, the standard estimate for 4 people runs around 8,000 pounds a year, roughly 48,000 pounds for the trip out alone, not counting the return. Add water, air, radiation shielding, and tons of electronics. Protecting against energetic solar particles and cosmic rays demands mass and serious engineering, and the psychological toll of that kind of confinement, with Earth reduced to a pale dot in the window,
is very real. That's why, as long as the logistics of keeping a crew alive for that long remain unsolved, we keep investing in robots instead. In the near and medium term, 2 missions should keep our curiosity fed. NASA's Europa Clipper, already launched and set to arrive around 2031 after a long route to safely enter Jovian orbit, and ESA's JUICE, which launches, runs its gravity assists, and arrives around 2029 for a dedicated tour of the icy moons. Notice, once again, the same pattern. To stay, the trip takes longer. To pass through,
Saturn. And Saturn. Who hasn't looked through a small telescope and held their breath at those perfect rings? They hide questions that don't fit in a single video. How they formed, why their colors vary, why the planet glows faintly on its own, how many more moons are still waiting to surprise us. The icing on the cake goes by the names Titan and Enceladus, one world with seas of methane, and another moon that shoots plumes of salty water out into space. But the first question is still, always, distance. And here too, everything keeps changing. At best, about 746 million miles. At worst, more than 1 billion. Cassini, which spent 13 years writing Saturn's encyclopedia, didn't fly there in a straight line. It made 2 flybys of Venus, swung back past Earth, took a boost from Jupiter, and only then dove into the realm of the rings. Pioneer 11 took more than 6 years. Voyager 1, on an excellent alignment, arrived in about 3 years and 2 months. Voyager 2 in about 4 years. Cassini ran a 7-year marathon to arrive already at the right speed to be captured. New Horizons, on a flyby trajectory, set a record, about 2 years and 4 months to cross Saturn's orbit. The reason for these differences is already clear. The chosen route, the number of gravity assists, the power of the engines, and above all, whether or not the mission needs to brake to enter orbit. And for humans, the same logic that complicates Jupiter makes Saturn even harder. A crew means multiplying the mass, a bigger capsule, supplies, life support, redundancy, shielding, instruments. Some estimates suggest a human itinerary could take 8 years just to get there, and the return trip would depend on an actual ballet, with Jupiter positioned perfectly to offer a gravitational slingshot back home. Not to mention the weight of radiation exposure, the psychological stress, and everything we're only now relearning how to manage through the Artemis program. That's why, for now, the most logical path is still to send robots and learn from them, one step at a time. Uranus and Neptune. At the outer edge of the giant planets sit two bluish worlds that look almost like twins at first glance, but tell very different stories once you get close. Uranus and Neptune. Today we know that blue doesn't mean oceans. It's chemistry, an atmosphere of hydrogen and helium seasoned with methane, ammonia, water, and hydrogen sulfide, absorbs red light and reflects back that blue-green hue. Uranus, in particular, is a collection of oddities. It spins on its side, with its axis tilted about 98 degrees. It has a magnetic field misaligned by nearly 60 degrees and offset from its center, and it seems to give off very little internal heat, a detail that might trace back to a major impact in its past, one that scrambled its internal layers and may explain its washed-out color compared to Neptune. Voyager 2's images from 1986 showed a calm, almost featureless disk with barely any bands or visible storms. Infrared telescopes later revealed that calm is only on the surface, but Uranus does remain the least turbulent of the giant planets. Neptune, by contrast, is pure motion, winds reaching up to 1,300 miles per hour, giant dark spots that appear and vanish, and an atmosphere so turbulent it prevents the kind of photochemical haze that mutes the contrast on Uranus. The moons tell the other half of the story. Miranda, Ariel, Umbriel, Titania, and Oberon, Uranus's 5 largest moons, show young surfaces and enormous cliffs. Verona Rupes may offer a sheer drop of more than 12 miles, along with signs of cold, icy geology instead of molten rock. When we look at exoplanets, it becomes clear why all of this has suddenly jumped up our list of priorities. Ice giants like Uranus and Neptune are extremely common around other stars. Understanding our own blue giants means understanding entire other planetary systems. That's why the scientific community has turned its spotlight toward a mission that already has a nickname: Uranus Orbiter and Probe. A dedicated orbiter paired with a probe meant to dive into the atmosphere. The most favorable launch windows fall around 2031 to 2032, using Jupiter as a slingshot, for a cruise time of about 13 years. Other, later windows require routing through the inner planets and push the trip past 15 years. The price, billions of dollars, and 2 decades before the first data even comes back. But it would be worth every cent. Fundamental science about how planetary systems are born and grow up. That leaves Neptune, a place so far away we've only ever seen it up close once. Yes, in the entire history of space exploration, only Voyager 2 has ever passed by, back in 1989. And it only managed that by catching an extremely rare alignment that repeats just once every 176 years. Jupiter, Saturn, Uranus, and Neptune all lining up in a way that lets a spacecraft chain gravity assists together without needing impossible amounts of fuel. A gravity assist works like a ramp. The spacecraft falls into a planet's gravity well, and if it doesn't crash, it comes out the other side with an adjusted direction and a speed boost, drawn from a tiny fraction of that giant's orbital energy. It's the only realistic way to visit several destinations on a single mission without hauling along enormous fuel tanks. The cost: you almost never get the chance to break afterward. And if you want to stay, you need to carry a massive fuel reserve just to slow down to match the planet's orbital speed. The braking math at Neptune makes that painfully clear. The planet orbits the Sun at about 3.4 miles per hour in space, 5.4 kilometers per second to be precise. Voyager 2, stacking assist after assist, was moving at about 15.5 kilometers per second by the time it got there, nearly 3 times faster. Capturing a spacecraft under those conditions would require an extremely long engine burn, and the fuel needed for a vehicle the size of Voyager would weigh more than 10 times the spacecraft itself. The process wouldn't take minutes. It would take 1 to 2 months of continuous braking, just for a lightweight probe. Now picture a crewed mission, a large capsule, shielding, years of supplies, redundant systems. The deceleration would have to be far gentler to avoid subjecting astronauts to dangerous forces, and the braking phase alone could stretch out over 2 to 4 years. Add that to the cruise time, and you're looking at 24 to 28 years between Earth and Neptune orbit, even taking full advantage of the best alignments and assists. And for the trip home, with current liquid chemical propulsion, the fuel needed for a round trip would turn the spacecraft into a literal skyscraper of propellant. More than 90% of everything that lifted off would be nothing but fuel tank, and we'd still be right at the edge of what's possible. That's why human missions to these far reaches remain, for now, firmly in the realm of someday, maybe, and will require an entirely different kind of propulsion. Pluto. Speaking of far reaches, there's one last, most famous ex-member of the club left to talk about. Pluto. Dwarf planet? Yes. Irrelevant? Never. So distant that the Sun looks like little more than a very bright star from there. Pluto traces slow, elliptical loops, sometimes around 30 astronomical units from the Sun, sometimes closer to 50. For us, that translates into cold, stubborn numbers. The Earth-Pluto distance typically swings between roughly 2.5 and 4.5 billion miles, with light itself taking anywhere from about 4 to nearly 7 hours to cross that gap, each way. In other words, any command sent today doesn't arrive until many hours later.
And the answer to that challenge is called New Horizons, a small, lightweight probe that traveled for 9.5 years at 10 miles per second to capture images of Pluto's frozen heart.
A crewed spacecraft, heavier and slower, would, in my estimate, need around 35 years to get there. 2 generations of astronauts taking turns at the window. Better choose travel companions you actually like for a trip like that. Closing. Throughout this whole journey, one detail keeps coming back. Being far away isn't just a question of distance, it's a question of energy. Changing orbits means changing speed, and every extra kilometer per second gets extremely expensive. That's why answers like 4 months to Mercury, 110 to 200 days for Venus, 9 months for Mars, a little over a year for a Jupiter flyby, but nearly 6 years to enter orbit there, 4 to 7 years for Saturn, depending on the route, over a decade for Uranus and Neptune. even in the most favorable scenarios, always need to be read with this caveat in mind. If the mission is just passing through, it goes faster. If it needs to stay, it slows down and carries an enormous amount of fuel. That's also why gravity assists remain the finest art in spaceflight navigation. The difference between a quick passing snapshot and an entire season packed with discovery. Can all of this be sped up? Yes. On paper, there are paths forward. Solar electric propulsion, cheaper, with a tiny but sustained thrust over time. Solar sails, a steady push from photons. Nuclear reactors, capable of generating continuous thrust. And bolder concepts still, like laser sails and next-generation ion engines. Each one solves a piece of the puzzle. Some cut down cruise time, others make the speed change on arrival cheaper. The engineering keeps advancing, one mission at a time. Meanwhile, we keep stacking up the lessons that got us here. The first close flyby of Mercury, detailed maps of its crust, the heroic final minutes of the Venera probes in Venus's hell, the Mars rovers turning the pages of history, Juno's dives through Jupiter's magnetic field lines, Cassini's long opera among the rings, the single, unrepeated passage past Uranus and Neptune, and the promise to go back, carefully, methodically, and ambitiously. In the end, the question, how long would it take to get there, is less a stopwatch and more an invitation to understand how the solar system actually works, and how we, these stubborn tool-using primates, are slowly learning to navigate this clockwork of gravity. Sometimes the answer comes in months, sometimes in years, sometimes in decades. And that's just fine, because every minute spent on the road pays back, 100-fold, centuries of knowledge when we finally come home. So here's the question I'll leave you with. If you could only choose one stamp to see up close, the shadow of Saturn's rings crossing its atmosphere, the cracks on Europa's ice, the calm of Uranus, the storms of Neptune, which one would you put in your cosmic passport? We just talked about Mercury as the world closest to the Sun, but there's actually a destination even closer than Mercury, one you might logically assume would be the easiest to reach in the entire solar system, since it sits right there at the center of everything. The exact opposite turns out to be true. The Sun holds 99.8% of all the mass in the solar system. Its gravity is what keeps everything in place, from Mercury all the way out to the Oort cloud, tens of billions of miles away. So why is it so hard to actually get there? Why can't you just point a spacecraft straight at it, cut the engines, and let it fall? The answer comes down to the exact same fact that's kept Earth from crashing into the Sun for 4.5 billion years. Earth is moving at roughly 67,000 miles per hour, almost entirely sideways relative to the Sun. That's not a fall. It's a fall that perpetually misses its target, over and over, and in doing so, traces out a stable orbit. To actually reach the Sun, cutting the engines isn't enough. You have to cancel out all of that inherited sideways motion, and canceling out motion, in physics, costs exactly the same amount of energy as adding it. Here's the number that messes with people's intuition the most. According to NASA itself, it takes roughly 55 times more energy to reach the Sun than it does to reach Mars. Take a second to let that sink in. The closest possible target in the entire solar system is also, in pure energy terms, one of the most expensive to reach. Some calculations go even further, canceling out enough orbital velocity to fall toward the center of the system would take almost twice the energy needed to escape the solar system completely and leave forever.
In a very real sense, it would be physically easier to abandon our star forever than to simply touch it. It's not a coincidence that, in Greek mythology, it was specifically by flying too close to the sun that Icarus fell.
The legend blamed the heat. Physics tells a story that's almost the opposite. Reaching the sun is nearly impossible to pull off, not because the sun pushes anything away, but because getting close to it means methodically canceling out everything that keeps us in orbit around it in the first place. The Forgotten Pioneers, Helios 1 and 2, before Parker's solar probe, before the public ever paid attention, 2 probes held this record in near total obscurity. Helios 1, launched on December 10, 1974, and Helios 2, launched on January 15, 1976, a joint project between the West German Space Agency and NASA, one of the rare international collaborations of that scale during the Cold War. The 2 probes were also the first spacecraft ever built outside the United States or the Soviet Union to leave Earth orbit. Both spacecraft dove into highly elliptical orbits, an aphelion close to 1 astronomical unit and a perihelion dropping to about 0.29 astronomical units from the Sun for Helios 2, roughly 27 million miles, slightly inside Mercury's own orbit, on an orbital period of just 190 days. On April 17, 1976, at that closest point, Helios 2 set a speed record that would stand for 42 years, about 157,000 miles per hour, or 70 kilometers per second. A record set by a probe that almost nobody outside of specialists has ever heard of. It feels a little unfair when you think about it. Voyager and Viking became household names. Helios accomplished work that was every bit as ambitious, and honestly more dangerous, since it was diving toward the furnace instead of the cold, and yet it stayed in the shadows for nearly half a century. Another strategy, Ulysses, and the angle no one had ever tried. There's a completely different way to tackle the sun problem. Instead of getting closer, change your angle entirely. That's exactly what the Ulysses probe attempted. A joint mission between NASA and the European Space Agency, launched on October 6, 1990, out of the cargo bay of the Space Shuttle Discovery. Up until then, absolutely every probe ever sent toward the Sun, Earth itself for that matter, and every planet, orbited more or less in the same plane, called the ecliptic. Nobody had ever observed the Sun's poles. The problem is that it's extremely expensive, energy-wise, to simply tilt a trajectory out of that plane. In theory, it would take almost as much thrust as leaving the solar system entirely. The solution, once again, was a detour. Ulysses first flew out to Jupiter, arriving in February 1992, and used the gas giant's gravity to literally fling itself out of the ecliptic plane, a maneuver of unprecedented precision at the time. It then passed over the Sun's south pole in June 1994 and the North Pole in 1995, revealing that solar wind, coming from the polar regions, blows in a surprisingly uniform way, at about 470 miles per second, more than twice as fast as the more erratic equatorial wind, clocked at around 220 miles per second. Designed for a 5-year mission, Ulysses ended up running 13 years longer than planned, completing several more polar passes before finally shutting down on June 30, 2009. It never tried to touch the Sun. It simply changed its angle, and that alone was enough to reveal an entire dimension of our star that no one had ever been able to see before. A quiet heir to Ulysses, Solar Orbiter. The polar detour strategy didn't end with Ulysses. Launched on February 10, 2020, by the European Space Agency in partnership with NASA, the Solar Orbiter spacecraft is pursuing the exact same idea, but this time with a camera trained on the Sun at all times. Rather than one single Jupiter flyby, Solar Orbiter works in small, repeated steps, a series of close passes by Venus, spread out across the entire mission, each one tilting its orbit a little further out of the ecliptic plane. On February 18, 2025, one of those flybys brought it within just 235 miles of Venus's surface, closer than the altitude at which the International Space Station orbits Earth. That slow, patient work finally paid off. In 2025, with an orbital tilt of about 17 degrees relative to the solar equator, Solar Orbiter captured the very first images in history, clearly showing one of the Sun's poles, a region no one had ever been able to observe directly before, hidden as it is from every planet orbiting in that same shared plane. Another Venus flyby is scheduled for December 24, 2026, another Christmas gift for the solar physics community, which will tilt the trajectory even further, with a final target of 33 degrees by the end of the decade.
Ulysses opened the door.
Solar Orbiter is keeping it wide open today, proof that the best way to understand our star isn't always to get closer to it, but sometimes simply to finally look at it from the right angle. Parker Solar Probe, the heir apparent. In 2018, NASA picked up Helios's torch with a far more radical goal, not just to approach the Sun, but to actually touch it, flying straight through its corona. The probe is named after Eugene Parker, the physicist who first theorized the existence of the solar wind back in 1958, making this the very first NASA mission ever named after someone who was still alive at launch. The problem remained the same one Helios faced. How do you shed enough of that sideways velocity inherited from Earth to fall toward the Sun without carrying a completely unrealistic amount of fuel? The solution was brutally elegant. Instead of burning fuel to brake, Parker Solar Probe used 7 flybys of Venus, spread out over nearly 7 years, borrowing a little of the planet's orbital energy on each pass to tighten its own orbit, again and again and again, 24 orbits in total, each one a little closer than the last. Launched on August 12, 2018, the probe had already, barely 2 months later, on October 29, 2018, become the closest artificial object ever sent toward the Sun, breaking Helios 2's 42-year-old record. And on December 24, 2024, an unusual Christmas gift for the mission teams, it reached its final closest approach, about 3.8 million miles from the Sun's visible surface, just 8.5 solar radii out. At that distance, propelled by the Sun's own gravity rather than its engines, it hit nearly 430,000 miles per hour, becoming, without question, the fastest object human hands have ever built. At that speed, you could cover the distance from New York to Tokyo in a little over a minute. Here's the important thing to understand. That record-breaking speed didn't come from a more powerful engine. It came from patience. 7 years of letting Venus, pass after pass, chip away at the sideways velocity inherited from Earth, until the Sun itself could finally do the rest of the work, accelerating the probe into its own fall.
No human being will ever be able to follow this route. Near the Sun, sunlight hits with roughly 475 times the intensity it does at Earth's orbit. enough to push exposed surfaces past 2,500 degrees Fahrenheit. Parker Solar Probe's heat shield, a carbon composite panel barely 4.5 inches thick, absorbs that inferno, while, just inches away on the other side, the instruments keep running at close to room temperature.
During the most critical minutes of each pass, the probe even loses all radio contact with Earth, too blinded by the sun's glare to aim its antenna, and has to operate in complete autonomy, on autopilot, trusting its own survival to lines of code written years in advance.
And all of that suffering serves a specific purpose: understanding why the sun's corona, its thin outer atmosphere, is, in a way that makes no intuitive sense, hundreds of times hotter than the surface directly beneath it. It's a bit like the air a few feet from a campfire being hotter than the flames themselves. That paradox, known as the coronal heating problem, remains one of the great unsolved mysteries of solar physics, and it's precisely to answer it that the probe keeps diving back into the furnace, mission after mission. Why this actually matters, here on Earth. You might reasonably ask why we'd risk entire spacecraft, for decades, just to better understand our own star. The answer comes down to a single event from more than a century and a half ago that still stands today as the benchmark for exactly what a solar storm can do. On September 1st, 1859, British amateur astronomer Richard Carrington was observing sunspots when he was suddenly blinded by a flash of white light on the sun's surface, the very first solar flare ever observed by human eyes.
Less than 18 hours later, a massive burst of solar material slammed into Earth, triggering auroras visible as far south as the Caribbean and literally setting fire to telegraph paper in stations around the world, the only electrical technology that existed at the time. Today, our entire civilization runs on electricity, satellites, GPS, and air travel. In March 1989, a solar storm far weaker than Carrington's was enough to collapse the entire Hydro-Quebec power grid in about 90 seconds, leaving 6 million people in the dark for nearly 9 hours. One benchmark study estimates that a storm on the scale of the 1859 event, if it hit today, could cost more than $1 trillion in the first year alone, with full recovery potentially taking 4 to 10 years, depending on how many transformers were destroyed.
Understanding why and how the sun unleashes these massive, sometimes unpredictable bursts of energy, that's exactly what Parker Solar Probe, Solar Orbiter, and all their predecessors are trying to figure out, one pass at a time. This isn't just scientific curiosity anymore. It's, quite literally, an early warning system for our entire modern infrastructure. So the next time you watch the sun set, never looking at it directly, of course, think about this. The closest object in the sky is also, of all possible destinations, the one that demanded the most twisted, the most patient, the most counterintuitive engineering of all. And speaking of working around a problem with patience instead of brute force, that's the exact same philosophy that let us reach our other closest neighbor a few decades earlier, Venus. Bonus chapter: the asteroid belt. Before reaching Jupiter, there's a region we tend to blow straight through without stopping, literally, since almost every probe that's crossed it was just passing through on its way somewhere else. The asteroid belt, that ring of rocky debris sitting between the orbits of Mars and Jupiter, roughly between 2.2 and 3.2 astronomical units from the Sun. An empty space that turned out to be full. On the very first day of the 19th century, January 1, 1801, Italian astronomer and priest Giuseppe Piazzi was scanning the sky from the Palermo Observatory in Sicily. correcting a star catalog. He noticed a point of light that shouldn't have been there, one that, night after night, kept shifting slightly.
At the time, astronomers were actively searching for a missing planet, predicted by a mathematical pattern called Bode's Law, in a suspicious gap between Mars and Jupiter. Piazzi believed he'd found that missing planet. He named it Ceres, after the Roman goddess of the harvest. But illness kept him from continuing his observations, and the object disappeared behind the sun's glare before anyone else could confirm it. It was the calculations of a young mathematician, Carl Friedrich Gauss, just 24 years old at the time, that predicted where and when Ceres would reappear, allowing astronomers to find it again on December 31st of that same year. That calculation helped establish the reputation of one of history's greatest mathematicians. Over the following 6 years, 3 more bodies turned up in that same region: Pallas in 1802, Juno in 1804, and Vesta in 1807. This wasn't a missing planet after all. It was an entire belt of fragments, the remains of a world that never managed to form, left behind as unfinished construction since the very birth of the solar system, torn apart by Jupiter's gravitational tides before it ever had the chance to come together. Forget everything Hollywood ever showed you. Before we go any further, we need to demolish an image. In nearly every science fiction movie, flying through the asteroid belt looks like a desperate slalom between giant rocks constantly slamming into each other. The reality is almost comically different. It's actually one of the emptiest regions in the entire solar system. If you gathered up every single piece of matter in the entire belt, every rock, every grain of dust, you'd end up with an object equal to barely 3 to 4% of the moon's mass. That tiny amount of mass is spread across such an enormous volume that the average distance between 2 asteroids larger than half a mile apart is several 100,000 miles, far more than the distance between Earth and the moon. If you stood on the surface of an asteroid and looked up, you almost certainly wouldn't see another asteroid with the naked eye, not even a single point of light. You'd need a telescope. That's precisely why about 15 missions have been able to cross the belt without ever needing a single avoidance maneuver. Pioneer 10 in 1972, the very first, followed by Pioneer 11, both Voyagers, Ulysses, Galileo, Cassini, New Horizons, Juno, and many others. The odds of a spacecraft accidentally hitting an asteroid while crossing the belt are estimated at less than 1 in a billion. Engineers planning these trajectories aren't trying to avoid asteroids. If anything, they often have to deliberately steer a little off course, just for the chance to photograph one along the way. A mission that never had a powerful engine. 2 bodies dominate everything else out there: Vesta and Ceres, which together make up about 45% of the entire belt's mass. And only one mission in the entire history of space exploration actually took the time to stop and study both of them in depth instead of just flying past. It's called Dawn, and the way it got there was radically different from anything else we've talked about in this video so far. Launched on September 27, 2007, Dawn spent more than a year methodically testing every one of its systems before performing a gravity assist off Mars on February 17, 2009. The same borrow some speed trick we've already seen at Mercury and Jupiter. But from that point on, everything about it was different. Dawn carried no powerful chemical engine capable of changing its trajectory in one quick burn. It carried an ion engine, the first purely scientific NASA mission ever equipped with one. An ion engine barely produces any force at all. Its thrust is roughly equivalent
to the weight of a sheet of paper resting in your hand. It takes about 4 days of continuous thrust, without a single break, just to accelerate the spacecraft from 0 to 60 miles per hour. That's ridiculously slow compared to the brute force of a traditional chemical engine, which delivers all its energy in a matter of minutes. But here's where the story flips. An ion engine never stops. It pushes, gently, for months, for years, powered simply by the spacecraft's solar panels, ionizing xenon atoms and firing them out at tremendous speed through an electrified grid. And over the full course of its mission, Dawn racked up a total velocity change of about 7 miles per second, more than any other spacecraft in history has ever managed using its own propellant, once separated from its launch rocket. An ion engine burns roughly 10 times less fuel than a conventional chemical engine to produce the same final result. Here, being slow isn't a weakness. It's the entire strategy. The first spacecraft to orbit 2 worlds. On July 15, 2011, Dawn entered orbit around Vesta, becoming the very first spacecraft ever to orbit a body in the main asteroid belt. It stayed there for 14 months, mapping the surface and discovering a dense core wrapped in a mantle and crust, an internal structure that looks a lot more like a rocky planet than a typical asteroid, along with an impact crater more than 300 miles across near its south pole, so massive it may have very nearly shattered the whole body. And here's the most surprising part. Fragments from that very impact had already reached Earth long before Dawn ever existed. An entire family of meteorites found on our own soil, known as head meteorites, had for decades carried a mysterious mineral signature that scientists suspected but couldn't confirm came from Vesta. By directly comparing the surface composition with those samples, Dawn finally closed that mystery. Those rocks, which had fallen from the sky long before the space age, had already been telling us, without our knowing it, the story of a world 125 million miles away. Then, in September 2012, thanks to that same patient engine, Dawn left Vesta's orbit, a feat no chemical-fueled spacecraft could ever have managed for lack of enough fuel reserves, and headed toward Ceres. It arrived on March 6, 2015, officially entering orbit on March 13th, becoming the first spacecraft ever to orbit a dwarf planet, and the first in history to orbit 2 separate extraterrestrial bodies in a single mission. What Dawn found at Ceres surprised everyone. The body may contain between 25 and 30% water by mass, mostly in the form of ice, and might even be hiding the remnants of an ancient liquid ocean beneath its crust. More than 300 bright spots were spotted on its surface, revealing unexpected geological activity for such a modest-sized body. In some ways, Ceres has more in common with the icy moons of Jupiter and Saturn, Europa, and Enceladus than with its rocky neighbors in the asteroid belt. The mission ended quietly, without any drama, in October-November 2018, when Dawn ran out of the hydrazine fuel used for attitude control, not for propulsion itself, after a total mission cost of about $473 million. Unlike other probes that are deliberately crashed into their targets to avoid biological contamination, Dawn was left in a stable, permanent orbit around Ceres, just in case that small icy world is hiding, somewhere beneath its surface, the conditions needed for life. It's still up there today, a silent hulk, endlessly circling a world it took 8 years to reach, not because of the distance, but because of a deliberate choice, patience over power. And today, Psyche, the air still in flight. That same philosophy is playing out right now, with a mission that hasn't reached its destination yet.
NASA's Psyche spacecraft lifted off on October 13, 2023, aboard a Falcon Heavy rocket, headed toward an asteroid of the same name, a world thought to be, quite literally, the exposed metallic core of an ancient protoplanet, stripped of its crust and mantle by a violent collision during the solar system's formation. First discovered in 1852 by Italian astronomer Annibale de Gasparis, the asteroid Psyche measures about 175 miles across at its widest point and may contain up to 60% metal by volume. Understanding its composition is a bit like getting direct access to what's hidden right now, beneath our own feet, at the very center of the Earth, a place we'll never actually be able to reach. The spacecraft also relies on solar electric propulsion, but with a different technology than Dawn's: Hall effect thrusters, a first for any interplanetary mission. The thrust they generate is so gentle it's roughly equivalent, according to NASA itself, to the pressure you'd feel holding 3/4 in the palm of your hand. And yet, over the full 6-year trip, covering 2.2 billion miles, that microscopic push will be enough to do the entire job. In May 2026, just a few weeks ago, as this video is being written, Psyche performed its gravity assist past Mars, using the exact same trick Dawn used before it, to slingshot toward the asteroid belt. It's expected to be captured by its target's gravity in late July 2029, and will stay in orbit there for 26 months, until October 2031. The spacecraft is also carrying a laser communications experiment, capable of transmitting data at speeds comparable to a home broadband connection, from more than 140 million miles away, a technology that could someday replace radio waves for staying in touch with future deep space human missions.
So somewhere out there right now, in the emptiness between Mars and Jupiter, a spacecraft the size of a tennis court is quietly accelerating, pushed forward by a barely visible blue glow, on a journey it started almost 3 years ago and won't finish for 3 more. Closer cousins, when you don't have to go that far. Not every asteroid visit requires crossing the entire main belt. An entire family of smaller bodies, known as near-Earth asteroids, orbits much closer to us, sometimes even crossing Earth's own orbit. And historically, these were the very first asteroids humanity ever learned how to approach, orbit, and ultimately touch. On February 14, 2000, a Valentine's Day that's still famous among planetary scientists, given that the target was an asteroid named after the Greek god of love, the American spacecraft Near Shoemaker became the first spacecraft ever to enter orbit around an asteroid, Eros. A year later, in February 2001, it did something even better than orbiting. It actually landed on the surface, a feat its own designers hadn't even planned for originally. Since then, Japan and the United States have run a kind of friendly race toward these small worlds. Japan's Hayabusa probe brought back to Earth, as early as 2010, the very first grains of dust ever collected directly from an asteroid's surface. Itokawa, its successor, Hayabusa 2, went even further. It actually fired a small projectile at the asteroid Ryugu to create an artificial crater and expose material buried beneath the surface, before bringing its samples back to Earth in December 2020. It's still out there today, headed toward new targets. NASA answered with OSIRIS-REx, which collected a sample from the asteroid Bennu in October 2020 and brought it back to Earth in September 2023. The first time an American spacecraft had ever returned material from an asteroid. By comparing the Ryugu and Bennu samples, the two space agencies discovered that these carbon-rich rocks share a common chemical history, likely born in the same distant region of the early solar system, before drifting apart on their own separate paths. Technically speaking, these aren't residents of the great belt between Mars and Jupiter. They're closer neighbors, stray rocks on orbits that sometimes brush against our own. But their story tells us the same thing Vesta's and Sirius's do. These tiny fragments, scattered across the solar system, may be some of the best surviving witnesses to what our neighborhood looked like before the planets even existed. And a third family, hidden in Jupiter's shadow. There's one last category of asteroids that rarely gets grouped into this conversation, and yet, Jupiter's Trojan asteroids. These aren't residents of the main belt, and they're not near-Earth objects either. They're tens of thousands of bodies trapped by the gravitational balance between the Sun and Jupiter, gathered into two swarms that lead and trail the giant planet along its own orbit, like two clouds of insects following a much larger animal. On October 16, 2021, NASA launched a mission named Lucy, after the famous fossilized skeleton of a human ancestor, 3.2 million years old, with a genuinely unprecedented goal: visiting 8 different asteroids on completely independent orbits over the course of a single 12-year journey. Never before, in the entire history of space exploration, had a single spacecraft attempted to reach so many separate destinations. Lucy has already tested its instruments along the way, flying past the asteroid Dinkinesh in November 2023, where it unexpectedly discovered a small moon orbiting it, and then Donald Johanson in April 2025. But the real journey doesn't begin until August 2027, when it reaches the first Trojan swarm, the one leading Jupiter, to fly past Eurybates, Polymele, Lucas, and then Orus in sequence.
It will then swing back past Earth one more time to pick up extra speed, heading toward the second swarm, the one trailing Jupiter, where it's set to reach the binary pair Patroclus and Menoetius in 2033, more than 12 years after launch.
These Trojan asteroids are likely direct leftovers from the cloud of material that gave birth to the giant planets themselves, genuine cosmic fossils, trapped for billions of years in Jupiter's gravitational shadow, never given the chance, good or bad, to become anything other than what they were on day one.
Once you've crossed this belt of debris and patience, the road continues toward a world that never needed patience to be impressive, because it's simply, overwhelmingly enormous. Bonus chapter: Beyond Pluto, into interstellar space. We just saw that New Horizons took 9.5 years to reach Pluto. But Pluto isn't the end of the story. 2 spacecraft, launched long before New Horizons, went even farther. So far that they eventually left the Sun's direct influence altogether. The Silent Elders, Pioneer 10 and 11. Before Voyager, there were the Pioneers. Pioneer 10, launched on March 2, 1972, became the very first spacecraft in history to completely cross the asteroid belt, then fly past Jupiter. In December 1973, Pioneer 11, launched a year later, repeated the feat before going on, in 1979, to become the very first spacecraft ever to fly past Saturn, literally paving the way for the route both Voyagers would follow right behind it. Both probes carried a gold anodized aluminum plaque, designed with help from astronomer Carl Sagan, a silhouette of a man and a woman, along with a diagram marking the Sun's position in the galaxy, in case some extraterrestrial intelligence ever intercepted them. These were the very first messages humanity ever deliberately sent toward the stars, long before Voyager's golden record, which would later take inspiration from them.
Today, both probes are silent. Last contact with Pioneer 11 came in September-November 1995. Pioneer 10 sent its final detectable signal on January 23, 2003, from a distance of about 82 astronomical units from the Sun. Neither one ever technically reached interstellar space. Contact was lost well before either crossed the heliopause, but both are still coasting, with no fuel and no commands left, on their own escape trajectories toward the stars. Pioneer 10 is drifting, very slowly, toward the star Aldebaran, in the constellation Taurus. It'll arrive there in over 2 million years. Pioneer 11 is headed toward the constellation Aquila, on course for an arrival in roughly 4 million years.
Voyager, the grand tour that wasn't supposed to keep going. Voyager 2 launched on August 20th, 1977, and Voyager 1 followed on September 5th of that same year, in that order, but on a faster trajectory. So Voyager 1 actually overtook its twin by December 15th, 1977. Their original mission covered only Jupiter and Saturn. It was only after completing that mission, taking advantage of a planetary alignment that only happens once every 176 years, that Voyager 2 pressed on alone toward Uranus and Neptune, while Voyager 1 headed off toward the outer edges in a different direction, having given up the chance to fly past Pluto in order to get a close look at Titan, Saturn's mysterious moon. On February 17, 1998, Voyager 1 became the most distant human-made object ever sent into space, overtaking Pioneer 10 at a distance of 69.4 astronomical units. On December 16, 2004, it crossed the termination shock, the boundary where the solar wind, previously moving faster than the speed of sound, abruptly slows down as it slams into the interstellar medium. Then, over the next 8 years, it crossed a huge transitional zone called the heliosheath, before finally reaching the ultimate boundary.
On August 25th, 2012, almost exactly 35 years after launch, Voyager 1 became the first human-made object to cross the heliopause and truly enter interstellar space, at about 121 astronomical units from the Sun. Voyager 2 did the same on November 5, 2018, at 119 astronomical units, on a different heading. To this day, these remain the only two spacecraft in human history to have directly sampled the plasma that exists between the stars. It took scientists nearly a full year to officially confirm the crossing had actually happened. The primary instrument on Voyager 1 capable of directly measuring plasma had already failed back in 1980. Confirmation only came thanks to a stroke of luck. A solar flare in March 2012 sent a shockwave all the way out to the spacecraft, causing the surrounding plasma to vibrate in a way that finally settled the question in September 2013.
Interstellar doesn't mean outside the solar system. Here's the nuance that changes everything, and that extends exactly the lesson running through this whole video. Crossing the heliopause means leaving the bubble of particles and magnetic fields the Sun projects around itself. It does not mean escaping the Sun's gravitational pull. The Oort cloud, that vast theoretical shell of icy bodies surrounding the entire solar system, starts somewhere between 2,000 and 5,000 astronomical units from the Sun, and may extend as far as 100,000 astronomical units. Voyager 1, despite having already traveled 121 astronomical units, won't reach even the inner edge of that cloud for about 300 more years, and it'll take roughly 30,000 years to pass all the way through it. In other words, the spacecraft has already tasted interstellar space, but gravitationally speaking, It'll remain a citizen of the solar system for tens of thousands more years. A bubble whose shape we still don't really know. Here's something remarkable. After more than 30 years of direct measurements, nobody actually knows for certain what shape this bubble the sun projects around us really has. For nearly 70 years, the scientific consensus was that the heliosphere looked like a comet, a rounded head out front, in the direction the sun is moving through the galaxy, trailed by a long tail stretching thousands of astronomical units behind us.
But more recent work, notably out of Boston University, has proposed a radically different picture. Instead of one long single tail, the heliosphere might actually look more like a deflated croissant, with two jet-shaped lobes on either side, shaped by the sun's own magnetic field, a much shorter, rounder, and far stranger shape than the comet image. Other, even more recent analyses, based on data from the IBEX spacecraft, seem to lean toward that same croissant hypothesis rather than the classic comet shape. The problem is that it's extraordinarily hard to settle the question. Only two spacecraft in all of human history, the two Voyagers, have ever directly crossed that boundary, and two data points simply aren't enough to map out the full shape of a bubble that vast. A new NASA mission, the Interstellar Mapping and Acceleration Probe, is now mapping this boundary from Earth orbit without ever physically approaching it, by observing particles that bounce back toward us from those distant edges. In other words, even the shape of our own cosmic home remains to this day an actively debated mystery. The communication delay, too, becomes almost absurd at this distance. Today, in 2026, a signal already takes more than 23 hours to travel between Voyager 1 and Earth, one way. On November 15th, 2026, just a few months from now, the spacecraft will reach an exact, symbolic distance, a full light day from Earth. At that point, a question sent from our planet will take an entire day to reach it, and the answer will take another full day to come back. Asking a question and waiting for the reply will then take exactly 48 hours. This isn't a conversation anymore. It's correspondence by letter, on a solar system scale. A slow fade, not a failure.
There's something strangely moving about the way Voyager 1 is approaching the end of its mission today. It's not going to break apart, or explode, or vanish all at once. It's fading out, slowly, like a candle running out of wax. Its 3 radioisotope thermoelectric generators, which convert heat from decaying plutonium into electricity, produced about 470 watts at launch, back in 1977.
Today, in 2026, they're producing only about 230 watts, a little less than half, losing roughly 4 watts every single year, without fail, for almost 50 years now. Of the 10 original science instruments the spacecraft carried, 7 have already had to be shut down, one by one, just to conserve the dwindling power supply. On April 17, 2026, engineers at the Jet Propulsion Laboratory sent the command to power down one of the last active instruments still running on Voyager 1, the one that had been measuring low-energy charged particles almost continuously since 1977. The command took about 23 hours just to cross the 15 billion miles separating us from the spacecraft. Today, only 2 instruments remain switched on, one that listens for plasma waves and one that measures the magnetic field.
The mission team hasn't given up, though. Right now, they're preparing a maneuver nicknamed internally the Big Bang, simultaneously swapping several power-hungry systems for ultra-low-power equivalents, hoping to buy a few more precious years. The test will run first on Voyager 2, in May and June of 2026, before being attempted, if all goes well, on Voyager 1 itself, no earlier than July.
If the maneuver works, there's even a chance the instrument that was just shut down could be switched back on. The stated goal is to keep at least one science instrument running well into the 2030s.
There probably won't ever be a big headline announcing the end of Voyager 1. Just, one day, a final signal that never comes, and antennas on Earth that keep listening out of habit to a silence that never breaks again. The youngest one, New Horizons, keeps going. There's still some good news in this family of aging spacecraft, though. New Horizons, the youngest of the group, the one that flew past Pluto back in 2015, is still making its own way toward the outer edge. On January 1st, 2019, it flew past Arrokoth, a small icy object in the Kuiper Belt, becoming the most distant object ever explored up close by a spacecraft, at over 43 astronomical units from the Sun. Based on current estimates, its power reserves should let it keep operating into the 2040s, with a long-term goal of eventually reaching the heliopause itself, sometime around 2040, if everything goes according to plan. 3 generations of spacecraft, 3 very different fates. The pioneers, silent but still in freefall toward the stars. The Voyagers, slowly fading out, watt by watt, after nearly 50 years of service. And New Horizons, still young, still full of power, having not even reached the boundary its elders already crossed. And if we kept going, all the way to the next star, Voyager 1 is currently moving at about 38,000 miles per hour. It isn't headed toward any particular star, but in roughly 40,000 years, its current trajectory will carry it to within about 1.6 light-years of the star Gliese 445 in the constellation Camelopardalis. At that point, it will become the human-made object that has ever come closest to another star, without a single human being ever having planned that encounter. And if, purely out of curiosity, we worked out how long it would take to cross the distance to the Sun's actual nearest star instead, Proxima Centauri, 4.24 light-years away, the answer would be roughly 75,000 years, 750 centuries, just to cross the distance to our nearest stellar neighbor. That's the kind of number that makes everything else in this video, the months to Mars, the years to Saturn, suddenly feel tiny by comparison.
So, can we do better? On paper, a project already exists, and it has a name that sounds almost like science fiction: Breakthrough Starshot. Founded in 2016 by investor Yuri Milner in collaboration with physicist Stephen Hawking and Mark Zuckerberg, initially funded with $100 million, the concept is genuinely audacious. Instead of one large spacecraft, a fleet of thousands of chip-sized nanocraft, each attached to an ultralight sail just a few yards across. A network of extremely powerful ground-based lasers would illuminate those sails for just 10 minutes or so, accelerating them under thrust equivalent to roughly 10,000 times Earth's gravity, up to about 20% of the speed of light, or more than 130 million miles per hour.
At that speed, the trip to Proxima Centauri wouldn't take 75,000 years anymore. It would take about 20 years. But there's a price to pay for that speed. These nanocraft would have absolutely no way to brake once they arrived. That would require something like a magnetic sail interacting with interstellar plasma, a technology that's still completely out of reach at the scale of an object weighing just a few grams. So it would be a flyby at full speed, lasting just a few hours. Enough time to capture whatever data is possible before continuing on, forever, into the emptiness beyond. Transmitting that data back to Earth would take about 80 hours during the peak approach window. The flyby itself is brief, but getting the information back down already takes several days. And once the data is collected, there's still another 4.24 years to wait, the time it takes light itself to travel back to us, before we'd see a single image. 20 years of travel, plus 4 years of radio silence. Almost a quarter century of waiting for a single passing glance at a world we'd never get the chance to see again.
The project remains, to this day, largely theoretical. Public activity around it has slowed noticeably since 2023, and no complete prototype has flown yet. But materials research continues behind the scenes, with ultra-thin sails being developed at Brown University and nanotechnology being tested at Delft University of Technology.
The physics itself still doesn't raise any fundamental objections, and that, on its own, is an extraordinary thing to know. Somewhere between the energy we know how to produce today and the energy it would actually take to reach the stars, there's no impossible wall in the way. There's just still a tremendous amount of engineering left to do.
Voyager, meanwhile, will keep traveling long after Earth has forgotten its name, long after its last signal, long after the people who built it are gone too. It carries, on board, a gold-plated copper record, designed under the direction of astronomer Carl Sagan. 116 images, encoded as analog signals, characteristic sounds of our planet, greetings recorded in 55 different human languages, and about 90 minutes of music drawn from a wide range of cultures and eras. The cover itself carries engraved instructions, how to play the record, how to decode the images, and a diagram that uses 14 known pulsars to mark the sun's exact position within our galaxy, in case, however infinitely unlikely, someone out there someday crosses paths with it in the dark and wants to know where it came from. That record will keep spinning silently in the void, long after the very last watt from its generators finally runs out. It hasn't been, for a very long time now, a space mission in the ordinary sense. It's a message in a bottle, thrown into an ocean so vast that no hand may ever pull it back out, and sent anyway. And maybe that's the strangest lesson of this entire journey. Some letters get written knowing they might never reach anyone at all, and we send them anyway.